Hi everyone. So today we're not starting with learning objectives because if you saw them, you'd have a fit. Um, Today we're going to be talking again about Newton's law of gravitation. Now you may remember that Newton's law of gravitation applies to two masses. So you have this big mass m, small m, and they're separated by a certain distance. Let's call it r. And remember, r is not the radius. R is the distance. If you want the radius, that's big R here. And we're not going to use it for anything at all. Now, remember that in this case, we treated these two masses as if they were a point mass. That is, as if all their mass was concentrated in one point in the middle. Well, okay, I tried to make this in the middle. That didn't quite succeed. But anyway, you may remember that Newton found out that the force between these two guys was given by this expression. So a minus, because remember the force is attractive, minus g big M small m divided by r squared. Some people include the minus, some people don't. That depends on whether you're using the vector expression or not. Anyway, so that was Newton's law of gravitation. It tells us the force between these two guys. But sometimes we're not interested in knowing the force between two guys, but what we want to know is, okay, imagine that I am here. So at this other distance, again I'm going to call it r, but I'm going to give it a different color. So now I'm here, and I don't know how much I weigh. But what I want to know is how much force per kilogram that I weigh will I receive from this guy. And remember, this was called the gravitational field. And since the gravitational field is just the force per unit mass, we had that G was the force divided by the mass of the guy that I put in here, and therefore was equal to minus G M divided by r squared. And hopefully everybody remembers this. So the field, remember, was defined as the force per unit mass. But today we're not going to talk about fields and forces, but we're going to talk about energy instead. So what we want to know is about the potential energy of two charges, two masses next to each other. And this is very similar to when we had two positive charges. Remember, we had two positive charges, one here, and then we said, well, if we let them go, they will gain some kinetic energy, right? Therefore, these two things have some potential energy. And we ended up defining potential energy as the work that we had to do to move the small charge from infinity to the point where it ended up. Now let me just add the distance here. So this is at a distance r. And this again has big mass m, this has small mass little m. Okay, so in this case we ask ourselves, how much work do I have to do to bring this mass from infinity to here? And this time these two guys are attracting each other. And because they're attracting each other, I don't have to do any work. If I just leave this guy, it will, on its own, reach this point, and then actually it will continue this way, right? So, in fact, I don't have to do any work. The work is done for me. Therefore, what we would say is that the work that I have to do is negative. And therefore, the potential energy of these two charges will be negative. Now, hopefully you will remember that the potential energy of two charges was calculated as the area under the curve of the force, but we couldn't do it because you guys don't know how to integrate. But we did arrive at this expression, right? K Q little q divided by r squared. And remember that the electric field and the gravitational field have almost the same expression. The only difference is that instead of k, we have minus g, instead of q, we have m, instead of small q, we have small m. Therefore, the potential energy for the gravitational field must be minus g, big M, small m, divided by r squared, which is the area under this graph. So if I plot F as a function of R, and I get something like this, well, in fact, I would get a negative. The area here with a minus sign would be this. Okay, so this is the potential energy of these two charges. Now remember that we don't really care about the absolute value of the potential energy, but what we care about is potential energy differences. So for example, if I know the potential energy here and the potential energy here, I can calculate how much work I need to do to bring this little mass from here to here. And that will be the difference between potential energies between here and here. And in this case, I will get a positive number because the difference will be positive. So don't be bugged by the fact that this is a negative number. It doesn't matter. All that says is that bringing together masses is for free. Actually, they help you. What is hard is to separate them. That's all you need to understand. But what if instead of potential energy, what I want to know is the potential energy per unit of mass that a certain mass in this point here would have? Well, again, let's assume that this is M, this is R. So what we really want to know is the potential energy per unit of mass. And how are we going to call this? Well, we're going to call it the gravitational potential, just like the electric potential. So the electric potential, remember, was potential energy divided by charge. In this case, we have potential energy divided by mass. Okay? So remember that was minus G M over R squared, and then divided by M. These two M go, and therefore we have that the gravitational potential is minus Gm divided by R squared, which looks exactly like the electric potential that we defined some weeks ago, just changing the constants. And that makes sense because the two forces have exactly the same expression. So you can understand the gravitational potential just like you do the electric potential. It's the potential energy per unit mass that a mass would have in here. And that's all there is to it. Now, take a good look at this, because this is energy per unit mass, and therefore this is not a vector, this is a scalar. And that's very, very, very good news, because look at this. I just love doing that. All right, so imagine that now I don't have one mass, I have three. So one here, one here. Oop. How did that happen? Okay, one here and another one here. And I want to calculate the potential in here. How do I do this? Well, if you had to do this with fields, you would be very, very upset, because you would have to calculate the strength of the fields, calculate the unit vector, then add up the vectors, and then find out the length. But now, this is just a scalar. This is just a number. So what do? We calculate the potential of this guy here, we calculate the potential of this guy here, then this guy here, and then we just add them all up. So remember, potentials add up, just like numbers, because they're scalars, they're not vectors. Now there are some very interesting relationships between the potential, V, and the field, G. And they are very, very similar to the ones that we already talked about when we talked about electric fields. Actually, they're exactly the same. So we can talk about something called equipotential lines. And where equi just means equal, right? So equipotential just means equal potential. Equipotential lines. And lines of equal potential, for example, around this guy, how are they going to look? Well, yes, I'm sure you said it in your head. Like circles that are concentrical to this little mass here, right? Okay. Yeah, okay. The last one was not a circle, was a potato. But you got the idea. So, all right, we have these equipotential lines, and where does the field point? Well, you know that it points this way. right? And the potential actually increases from the center to here, because remember it's negative, but it's much more negative here than here. Here it's almost zero. So the potential increases from here to here, which means that masses want to go always towards lower potential through the fastest possible path, which is crossing perpendicularly the equipotential field lines. And this, again, happens for any potential of any force and for any field lines of that force. They will always be perpendicular to the equipotential lines. So what happens if, for example, we have two masses? So well, let's draw it. I have mass number 1 here. Okay, maybe I should put it somewhere else. There you go. And mass number 2 here. And in this case, well, if we're very close to the mass, they won't really see each other, right? And as we get more separated, something like this will happen, right? Okay, so what's going to happen to the field? Well, again, same thing. Like this, like this, like this, always perpendicular to the equipotential lines. Very entertaining to draw this. And it's something that you will also have to do. So pay attention. Now I'm going to give you a mathematical expression that relates G, the field, and V, the potential. Now, unfortunately, I cannot prove this to you because you would need to know calculus, integrals, and so on. And you just don't. So what I'm going to do is something really quick and dirty to show you that this relationship is plausible, and then hopefully when you know how to do integrals, if you ever do, you will be able to derive this yourself. So imagine that I have a certain mass in a field. So here's my little mass, and there's a field. And what I'm going to do is consider that the field is uniform. So for example, we're very close to the surface of the Earth, and the field is more or less the same everywhere we are. Okay, so this is the Earth. Our mass is here, and the field all over the place is constant. Okay? So now I want to know how much work I need to do to move this guy from here to here, a distance increase in r, right? Because remember, r is the distance to the center of the Earth. So there's a certain increase in r. Okay? Well, in this case, the work that I have to do will be work, and it's going to be the force times the distance, right? And how much is the force? Well, mg. All right. So mg times the increase in distance. Now, what can we do with this? Well, what we're going to do is isolate g. So we go and say that g, well, wait a second. All right, that's going to be better. So work equals mg times the increase in r, and therefore g equals work divided by m and divided by the increase in r, right? But if you look at this, the work that I have to do is exactly the opposite of the increase in potential energy, right? So let's say this is equal to minus the increase in potential energy divided by the mass divided by the increase in r. And now remember that the potential energy per unit of mass is nothing but the voltage. Yeah, the gravitational potential. In this case, it's not really the voltage because there's no electricity, but the gravitational potential, right? Or in this case, the increase in gravitational potential. And therefore we get that G equals minus the increase in gravitational potential divided by the increase in R. Now, we're not done yet. In order to prove this, we had to assume that V and G both change very, very, very little. Now, this is only going to happen if this increase is extremely small. How about, and actually this is going to be exact, when this is infinitely small. Now you guys know, now that you know derivatives, that an infinitely small increase is a differential, right? So we can rewrite this formula as minus dV dr. That is, if I know the potential that a charge or set of charges produce, I can find the field by deriving like this. Another way to say it is, the field is the derivative, well, minus the derivative of the gravitational potential. And this also goes for the electric field, by the way. Now we're going to talk about something called escape velocity. And the idea is, imagine that I have a planet, and I have a rocket or whatever, or a ship here. So here's my rocket, and I want to send the rocket away from the orbit of the planet. Now, in order to kick this guy away from here, I need to give him some kinetic energy, right? What if I give him very little kinetic energy? Well, then it's going to go up, then it's going to lose all of its kinetic energy, and then go back down. What is the only way to make sure that this guy never goes back down? Well, if this guy has enough kinetic energy to go from here to infinity, then this guy will never leave, right? So the kinetic energy of this guy has to be equal to the difference in potential energy between here and infinity. Okay, so let's see how to calculate that. Well, remember that potential energy of a gravitational, well, two gravitational bodies was minus G m divided by R, right? Okay, so what we want to know is the difference between the potential energy when this guy is at infinity, so R equals infinity, and when this guy is here, so when R equals big R, which is the radius of the Earth or the planet where we are. Okay, so let's calculate that. So we have that the difference in potential energies will be equal to the potential energy at infinity, so this divided by infinity, I know it's a little ugly mathematically, but it works, minus Gmm, and this time divided by R, which is the radius of the planet. Now, this one here, something divided by something infinitely big, which is infinite, will be 0. And then minus minus, that's plus, right? So the difference in potential energies will be equal to Gmm divided by R. Okay, so now we know that at the very least, if we want this guy to escape, we will need to give him this much kinetic energy. But we're not interested in the kinetic energy, we're interested in the velocity, because remember, this says escape velocity, it doesn't say escape kinetic energy. So let's calculate that. All right, now we've got that this much potential energy is the kinetic energy that we have to give this guy. So therefore, 1/2 of m times the escape velocity squared, which is the kinetic energy that it must have, has to be equal to Gmm divided by R. And now what we need to do is cross things out. M and M go. And so we get that escape velocity squared is 2Gm over R, and therefore the escape velocity is the square root over 2Gm over R. Done. And you should be able to do this yourselves too. Okay. Now we're going to use what we learned to calculate something called the orbital speed. And the orbital speed is just the speed of the orbit. So I have a little mass here, let's call it m. M. And this one's called big M. And they're at a certain distance r, as always, and this one's moving around like this, right? Now we want to know, for this guy not to fall, what must his orbital speed be? And this is really easy if you know anything about circular motion, which I'm sure you do. So, do you remember what the centripetal force was? The centripetal force was the force that you need to do something if you want to keep it moving in a circular motion, right? Well, in this case, there's only one centripetal force. What is it? Gravity. Yeah, exactly, gravity. So, we know that our centripetal force is gravity, which is G, just in modular. I don't care about the sign now. Gmm divided by r squared. And that centripetal force has to be equal to mv squared divided by r, which is the expression for centripetal acceleration times the mass, right? Now, the first thing that we see is that the masses cancel out, which is great. This means that I don't care how heavy my satellite is, if it's at a certain r, it will go at the same speed as any other satellite that's at the same r, which is great. Okay, now since I'm interested in the orbital speed, all I need to do is isolate v. And again, I get, well, first thing, these r and these squared go, so out. And finally then, I get that v squared equals gm over r, and therefore v equals square root of gm over r. And that's my orbital speed. See, just by knowing a little bit about circular motion, namely the centripetal force, you can work this out. You should be able to do this yourselves, even though I've just derived it for you. You should be able to just re-derive it anytime you need. Alright, so now let's continue. Now we know that the orbital speed of a satellite is square root of gm over r, right? So what's its kinetic energy going to be? Well, kinetic energy is 1/2 mv squared, right? Yep, so kinetic energy is 1/2 times m times this squared, which is, so this thing squared, which is just the same, the thing that's in the square root, right? So times gm over r. And look how cool this looks. This is gm m over 2r. Does that look familiar? Well, actually, this is the same as saying 1/2 of gm m over r. And this thing here is nothing but minus the potential energy, right? So therefore, we have that the kinetic energy is minus 1/2 of the potential energy of the satellite. Isn't that wonderful? The things you discover. This is just a smiley face because we still have 2 slides to go, and I think after all this you must be a little tired and feeling a little frustrated. So there you go. Smile. Almost done. Now, if you're a guy that is into astronomy and likes planets and stuff like Kepler was, what you're really interested in knowing about a planet is how long it takes it to go around its orbit, right? So how long is a year for that planet? So for example, a year of Earth is 365 days, and so on. So what this guy tried to figure out and did was how long it would take a planet at a certain distance to revolve around the sun. Now, there's many ways to deduce this, and I encourage you to try to do it yourselves before I do it, because it's really very easy. I'm just going to do it one way, but again, I could have done it anyway. Now, we know that the speed of a satellite, remember, was square root of gm over r, right? Now, just knowing this, we're pretty much set. For example, we know that the period, which is what we're looking for, is going to be the perimeter of the orbit, which is 2 pi r, right? Divided by the velocity, which we just have over here. Okay, so all we need to do is substitute. So 2 pi r over square root of gm over r, and that's going to equal 2 pi over square root of gm, and then this is dividing in the division, so it goes multiplying. So this r to the 1 plus 1/2, that's 3/2. So times r to the 3/2. Another way to put this is squaring the whole thing, and you can see that t squared equals 4 pi squared over gm times r to the 3. And this is Kepler's third law. What it says is that the square of the period is proportional to the cube of the distance. And that's it. Okay, one last thing and we're done. Now imagine that I'm here in my square rocket and I'm orbiting the Earth, going like this, right? And I want to know how much gravity do I feel, right? Now, what I feel really is not the force of gravity, but it's the force of the Earth pulling me up, because gravity is trying to pull me down, and then the Earth counteracts and then pulls me up, right? So what I'm really feeling is the normal force of the ground. So if we want to know how much gravity I'm actually experiencing here, we need to take a look at the normal force that I experience from the ground. Okay? Now, turns out that both me and my box are moving at the same speed, right? So therefore, what's the relative acceleration of me and my box? Well, that's 0. But therefore, if my acceleration respect to this box is 0, what's the force between this box and I? Well, that's 0, right? Therefore, how much gravity do I experience when I'm in here? 0. Does this mean that there's no gravity? No, there's gravity. Of course there's gravity. Otherwise, I wouldn't be describing an orbit. But I experience weightlessness in the sense that I seem to be floating in my box, just because both I and my box are moving at the same speed. If this was not an orbit, but we were just falling in free fall, this would be even clearer, right? I'd be falling down, so there's definitely gravity. The box will be falling down, there's definitely gravity. But from my reference frame, I would see my box and I always at the same distance. So I wouldn't feel any acceleration towards the bottom of the box. And therefore I'd say, oh, I'm weightless. Now, this insight that being in free fall is the same thing as feeling weightless is what was used by Einstein to elaborate his general theory of relativity. And it turns out that it's a very, very deep insight about the way the world works. For the moment, though, it's just a marvelous coincidence. Right, I hope you survived this video. I barely did. Now, this is the list of learning objectives that we had, and it's going to take us 2 weeks to just do enough problems to be comfortable with this. But you should already be able to do all of this, or at least you should have seen all these things. So, define gravitational potential energy, check. State and apply the expression due to a point mass, check. This we've also done. Determine the potential to one or more point masses, we've also done. Remember, they just add up. Sketch the pattern of equipotential surfaces, we've done this. We also know the relationship between them and field lines. We also know what the escape speed is and how to calculate it. So we've done that too. This remains to be seen. State that the gravitation provides the centripetal force for circular orbital motion. Yes. We've also derived the third law. We've derived expressions for the kinetic energy and the potential energy and the total energy of an operating satellite. Well, actually, I haven't done the total energy, but I'm sure you can figure it out. Sketch graphs showing the variation. No, we have not done this. I hope you will be doing this during the problems. This we've done, and this you'll be practicing these next 2 weeks. So good luck with that. This topic is not easy. This topic is higher level. I'll be there to help. See you soon.